In this video, we will try to solve this problem using involving inequalities in the integrals. Basically, in this problem, there's really no use of integrals. Just the Jensen inequality will be enough. And this was proposed by Isabel, Dıaz-Iriberri, and Jose Luis Dıaz-Barrero, Barcelona, Spain, in the School Science and Math Journal, like a few years back. And this states that the function is has domain 0 to 1 and range as real numbers, and this is a convex function. So this is an important thing to notice, that this is a convex function. So that's why in Jensen inequality, what happens is, basically, if we have f of x like convex in some domain, that means like this. So in this case, what happens is, let's say f of a plus f of b plus, let's say there are three variables, f of c by 3. The average of three variables will be greater than equals to f of a plus b plus c by 3. This is Jensen inequality. We will try to use this thing to prove. Now, a more general Jensen inequality would be, let's say there's x times f of a. There are x numbers of f of a and there are y numbers of f of b. So in this case, and if we divide by x plus y, this will be greater than equal to there will be f of, there will be x a's and y b's by x plus b. So this is the inequality in general. Now let's begin solving the problem. So in this problem, first of all, we will try to make all the inequalities go from 0 to 1, and then we can deal with just the functions only. Okay, first of all, let's do that. So now for this one, if we do let's say y equals to 5t, this will go from 0 to 1. Now if we say that this y equals to 5 by 2t, in this one y equals to 40. Let's do that. And now 3 by 4 integral goes from 0 to 1, and now our t is y by 5, f of y by 5, and now dt will be dy by 5. Okay, plus 1 by 8 integral from 0 to 1. Now f of that will be 2 by 5 y, 2 by 5 y, and then d 2 by 5 dy. Okay, now this will be greater than equals to 4 by 5 integral from 0 to 1. Now that will be f of y by 4, and then dy by 4. Now we can cancel the 5's from all of the terms. So this will be 3 by 4 integral from 0 to 1 f of y by 5 dy, and then this will also be 1 by 4 integral from 0 to 1 f of 2 by 5 y will be greater than equals to, this will be 1 integral from 0 to 1 f of y by 4 dy. Now I can write this as integral from 0 to 1 3 f of y by 5 plus 1 f of 2 by 5, and by 4 is greater than equals to integral from 0 to 1 of f of y by 4 dy. Okay, so now next what can we do? Okay, so basically this is 2i by 5, I'm sorry. Now so we can also take this constant inside the integral. Yeah, and now since we know that from 0 to 1, from y going from like the domain going from 0 to 1 and up to r, we know that here also the domain of all the functions, yeah, basically it's from 0 to 1. Yeah, so in while y is going from 0 to 1, let me write dy as well. While y is going from 0 to 1, all the domains in the functions are basically from 0 to 1 itself. Yeah, so you can see that because these are like some fractions, proper fractions. And so in this range these functions are convex. So what we will try to prove this, basically we can try to prove this thing: 3f of y by 5 plus 1f of 2y by 5. Now this expression over 3 plus 1 is 4 using Jensen inequality is greater than equals to, now what can we do, like multiply 3 times y by 5 plus 1 times 2y by 5 by 4. Okay, so now this will be equal to f of, this is 5y by 5, yeah, that's just 1, and so y by 4. And now we have proved this expression. Now we can just take integral on both sides from 0 to 1. Yeah, because in this range the inequality was actually holding in this range itself, so we can now apply the integrals, and so we have proved it. Yeah, so this was it. This was just a direct application of Jensen inequality after making the limits of integral same. Yeah, so we can do it for the inside terms. And yeah, I do hope you enjoyed this application of Jensen inequality for this problem. And yeah, thanks for watching. Look forward to seeing in the upcoming videos too.